Hello and welcome to part 2 of the KIM-1 Resurrection series. In this video I'll be covering the beginning of the 64 channel logic analyzer that I need to build before I can even start fixing the KIM-1. As I mentioned in our previous videos, the logic analyzers I've got don't have enough channels, or they're not fast enough. So I've revisited my sort of logic analyzer from the homebrew CPU series and improved it, changed the processor and how many inputs, etc. Now if we have a quick look at the KIM-1 manual, you can see there's quite a lot to the KIM-1. This is just the hardware manual. You go through it, you've got all the information here about how it all works, all the circuit diagrams, etc. So hopefully with all this I should be able to figure out what's wrong and make it work, and that is just the hardware manual. There's also a user manual to this as well. There's for a single board computer it's quite a complicated little beastie. It just so happens this turned up yesterday morning. In here should be some nice circuit boards. There we go. Chuck that out of the way. This is the first prototype. Hopefully I've not made any mistakes in it. So let me get these out here. Oh, I pack them in very securely. Oh dear, what's happening there? Alright, so got 5 of them here. I need the one, hopefully. And you may recognise this from the circuit I showed you in the last video. Lost my pointy stick, I used my pen instead. So we got, here's your inputs coming around the side. There's 64 of them in all, plus 2 more trigger ones down here. Let's bring it over here so you can see it better. So here's your inputs, input 0 upwards, and they're in like groups. So this is one word, so 16 bits can come in there. That's word 0. And then you've got word 1 would be these 2 here, and then word 2 be those ones, and then word 3 would be these ones. So if we're in 16 channel mode, we'll just read these ones up here. In 32, we'll read those 4. If in 64, we read all 8 of those. Now this here is a extra one, that's just for T0 and T1. They're the triggers on a separate port, so you'd have a separate lead for your trigger. And I'll remember to put some volt links in as well. This is just the programming port for putting the programmer in. And these here, there's all the weird mistake on here. That says 16 meg there. It should say 12 meg. But this is like default settings for when you start up. So it needs something in there. So you'll have 3 jumpers in here at least. One on the channels, one on the frequency. And, well, not necessarily on the triggers, but we'll go through that shortly. And there's your serial port should sit on top of there. And there's your power regulator to give me the 3.3 volts for the microcontroller in here. These resistors all around here is for reducing the 5 volt signals coming in down to 3.3 volts for 3.3 volt controller. So if we get close up without getting out of focus, as you can see, it's got some very small connections on there. They're 0.5 millimeter apart, so I'm going to have great fun soldering those. And there's no components on the back. What I'm going to do is I'm going to 3D print a little base for it so it fits on it, to make sure the back is fully insulated, so when you're using it and it gets pulled around because the leads might not be long enough, it won't short anything out, because these pins will all be soldered up and you could short things out. So you can get it on the light there. You can see some buses running around the back here feeding the data around. That's the board. It turned up just in time. So if we pop back to where we were on here, I'll go over how this system's meant to work. The design was meant to be 64 channels at 4 megahertz, or 4 million samples a second. So that's the goal, but I've enabled some other features on it because I could. It's just a matter of tweaking the software. So we can be in 16 channel mode, and we get 30,000 samples in 16 channel mode. And we can run any of these frequencies from 12.5 megahertz down to 1 kilohertz. It says 12.5 and 8.33. That's because the number of steps on the microcontroller, I can't actually get it to be exactly 12 meg. 12.5 was the nearest I could get. I think that's 8 cycles, 100 MIPS. So you get 12.5, which is okay. It's a bit faster, and 8.33. And all the rest are nice round numbers. And if you're in 32 channel mode, you can only get 15,000 samples because there's twice as many channels, same amount of memory. But you can't do that at 12.5 megahertz. It's just not fast enough. So you could sampling twice as much, you can only do it half as often. So you've got those frequencies available. And the target was 64 channels. And you can have 7,500 samples there. And they're all the frequencies you can run that at. If you happen to set it 64 channel and 12 megahertz, you just won't do it. The software will go, no, that's bad. So, and then there's 2 independent triggers on there, T0 and T1. Now these can both be independently set as positive edge or negative edge. So you can have one of them as positive and one as negative, or both positive or both negative. And if either of them trigger, that's when the software will start sampling. Now this is going to plug into the PC via the serial port. And there will be a piece of software between the Logic Analyzer hardware and the Pulse View software to view the data. I don't know how to write a driver for Pulse View to talk to it direct, so I've had a look at the input facilities on Pulse View, and there's a comma separated variable format which I'm going to use. So I'll write a little bit of software in BASIC, haven't even started that yet. And that will send these possible commands. So if it sends a string that says 12 megahertz, it will switch the analyzer to 12 megahertz speed. 8 megahertz will put it to 8 megahertz speed, and so forth. And you can set what channels you want, whether you want it 16, 32 or 64, by actually sending that string to it. And there's T0 positive, will set trigger 0 to positive edge, and so forth with the others. And then there's the 2 final commands, arm and disarm. Arm means everything's configured, watch the triggers, and if you see anything, start sampling. The disarm command is you can tell it not to do that and just go back to standby. Changing any of the other values like the sample rate or the edge or the channel numbers, that will actually disarm it as well. And when these commands come in, it will set a flag that corresponds to that value. So when you set it to, say, 4 megahertz, all the other sampling speeds will be turned off and only the 4 megahertz flag will be on. And same with the 3 channels options. Only one of them can be on at any one time. But the T0 and T1, you can either be positive or negative on each of them. So, the main sequence, the code on the microcontroller has got 2 streams. There's the main sequence and there's the serial interrupt sequence. Let's look at the main one to start with. This is the one that actually collects the data. When you go into it, it will start scanning to see whether it's been armed or not. If it's not armed, it'll just sit there. So it scans a flag called arm. This bit here, we're just scanning a flag in the software going round and round and round. When that flag comes on, it says, oh, I'm armed. So it then starts to scan the triggers. So it's going to look at the input of T0 and T1 and see whether they comply with what they were configured to. If they're both set to positive and they're set to negative, nothing happens, just goes round and round in a circle. But as soon as one of them goes positive, it'll go, oh, I'm triggered. And it'll go to, let's start reading the inputs. So if you're in 16 channel mode, you just read port 0 and you read that in 30,000 times. If you're in 32 channel mode, you'll read ports 0 and 1 and read again. There you do 15,000 samples there. And if you're in 64 channel mode, it will read port 0, 1, 2 and 3. And have 7,500 samples to fill up your 60 kilobytes of memory that we've got. And once that's all sampled, it will then transmit the data out of the serial port. It will actually transmit a header first of all, and then explaining the sample rate, etc. And then it will transmit the raw data, which is just be a series of bytes. So there's 64k of raw data, or sorry, 60k of raw data will go straight out after the header. Once it's done that, it will clear the armed flag and go back to the beginning and wait for it to rearm it. And that's the main sequence, just does that round and around. When you're reading the inputs, there's several blocks of code depending on whether you're doing 16, 32 or 64 channels, and also what sample rate you are. It sort of splits it off into different ones. Running parallel to this on the processor, it's just sitting there waiting for the interrupt to happen. Once you get a serial interrupt, it will read the serial port, read the byte in. If it gets an escape, come in 27. Sees a 27, it clears everything back and just clears all the buffer out and goes back to the beginning. You won't actually be typing anything in the software, you'll just be clicking on buttons, etc. And the basic program that's controlling it will send all the commands. So if it receives here a carriage return, which is a number 13, I believe, and it goes, oh, I've had a string sent to me, let's go and check it out. If you get in a 13, it says you've had a command come in. So it then decodes the command to try and decide what it is. Now the commands, if we quickly whiz back here, these are the actual commands. So these are the strings it will be sending. And if it recognises one of them, it sets the appropriate flag for that command. If we've got, now we get 16 channel string comes in, it actually says that. It'll clear the two flags for these two and turn that flag on. And if we get, say, a 2 megahertz here, it will clear all these flags and then set the 2 megahertz on. If it doesn't recognise it, it'll just clear the buffer and go back to the beginning again. So, set the appropriate flag and clear the buffer after you set the flag and go back to test whether the serial port is. I mean, you just return from the interrupt routine. I should have put an arrow there and saying return. The data that's going to be converted in the basic program. I haven't actually done this yet, but I've got all the ideas in my head. So there's a basic program that's, you'll have a series of buttons and that, so you can set what frequency and so forth you want and arm the analyzer. And then when the analyzer has found some data, it'll spit it out the serial port into the basic program, and it will read the header first of all, and the header will say things like we've got here. It will say this to start with to let us know what it is, and then it will say 16 channel 4 megahertz. So you know how many channels it is, and you know what frequency it is. So the idea of this bit here is so that the basic program knows the format of the data coming in, because it's going to be raw data. So you'll get that, and then you'll get the raw data. If you're in 16 channels, it'll be 2 bytes per scan. So it knows the first 2 bytes is 0 to 15 input, and then the next 2 bytes after that will be 250 nanoseconds later. So it knows it's all in just 16-bit pieces. If it was 64, it will be like 8 bytes per scan line. And it's always that number of bytes coming in. So that's going to convert that to a comma-separated value file, because PulseView can import that. Now the exact format I'm not sure of yet, I'll still need to decide which is best, but this is the general idea. First of all, it will sound like this. I think there might be a string at the beginning saying header or something, but it'll have these, and these are the names of the inputs. They could be anything. You could have D0, D1 or anything you like, but there'll be 16 of them, and then there'll be a carriage return, so at the end of the line. and then it will send the data, and so there will be 16 bits sent through, then a carriage return, then the next 16. So these 2 bytes here constitute these 16 bits here, all in the correct order, and then that's the next scan 250 nanoseconds later, and so forth. And it can do all that until the whole 60,000 bytes come in, and it will send this all out to a file, just an ASCII file. And in PulseView, we have to go to the import function and import this file, and that'll be all your code. So the serial port is running at 115 kilobaud, so that's 10,000 bytes a second. So it should take us around 6 seconds to transmit all the data to the basic program, which hopefully will save all this out in less time than that. Depends on the speed of your processor, your PC that is, and then the file will be ready to import into PulseView. It's it's an extra stage, but as I said, I can't write a driver for PulseView. I just don't have a clue where to look. I've looked through their files and that, and it doesn't seem to explain how to do it. So that's how far we've got so far. We've just got the boards, and in the next video you can watch me try and solder them together. A quick one for this episode, and don't forget to like and subscribe, and I hope to see you in part 3.